chemistry. We're moving on to lesson 13 of the foundations unit, and this has to do with the atomic radius. So atomic radius is half the distance between the nuclei of two bonded atoms, identical atoms. It's roughly the distance from the nucleus of an atom to the valence electrons, to the outer orbital. So that's the way we're really going to think of it. It's just like the radius of a circle. It's from the center to the outside of the circle, and that's the way we'll think of it. It's from the nucleus to the outside of the atom. But technically, it's the half the distance between two bonded atoms, because the valence orbital is not a very specific distance away. It's kind of fuzzy. So that's the way it's officially defined. Atomic radius is important because some chemical properties depend on whether an atom can fit into small spaces. So atomic radius decreases as you go up a group and to the right in the period. So it's the exact opposite of ionization energy and electronegativity, and we're going to talk about why that is. Okay, so the atomic radius, or radii, which is the plural of radius, are highest when an atom has more orbitals, the nucleus has fewer protons. So let's go ahead and look at these. So the first one, let's look at fluorine. Fluorine in the upper right-hand corner has the smallest atomic radius of those elements that you see on the screen there. Helium and neon actually have smaller atomic radii than do fluorine, but of those listed elements there, fluorine is the smallest. So bromine has a larger atomic radius than fluorine because it has 4 orbitals compared to only 2 for fluorine. So that explanation is pretty obvious. As you keep adding orbitals, the atom becomes bigger and bigger, and the radius, which atomic radius really means the size of the atom, becomes larger and larger. So that one's pretty easy. More orbitals is going to make the atom bigger. Now lithium over there on the left has a larger atomic radius than fluorine because it has the same number of orbitals, but fewer protons. So lithium does not pull electrons as well as fluorine. That's the same explanation you heard for ionization energy and electronegativity. But this one is a little counterintuitive. Lithium, let's just count. The typical lithium atom, the most common isotope, is going to have 3 protons, 3 electrons, and 4 neutrons. And that's a total of 10 particles. Now you go over to fluorine. Fluorine is going to have 9 protons, 9 electrons, and 10 neutrons. That we figured that out when we constructed that atom. That's a total of 28 particles. So lithium only has 10 particles, electrons, protons, and neutrons, and fluorine has almost 3 times as many. So why would fluorine be smaller than lithium? That doesn't seem to make sense. But it does when you think back to what we've talked about. The protons, fluorine and lithium both have the same number of orbitals, but fluorine has more protons in its nucleus. That puts a stronger pull on all of its electrons. So its electrons get pulled in more tightly, and therefore that makes fluorine a smaller atom, have a smaller atomic radius than lithium over there on the left. So it has to do with the number of protons. More protons pulls the electrons in more tightly. Lithium has fewer protons, neutrons, and electrons. However, the electrons are not held that tightly because lithium only has 3 protons. And of course, we talked about its Z effective number is only 1. So therefore, it's not going to pull any of its electrons in as tightly as fluorine, and that's going to make it a larger atom. So the second period elements show that lithium is much larger. So this is kind of a nice little chart that shows you the relative sizes of the atoms. And you look up there in the second row, you see number 3 over there in the upper left, or near the upper left, lithium, is much larger than if you go over to the other side where you see fluorine and neon over there on the far right, numbers 9 and 10 of the second row. I mean, it's not just a little bit bigger, lithium, it's much bigger than either fluorine or neon. Again, the number of protons increases as you go from left to right, even though the number of orbitals stays the same. So the electrons in both the first and second orbitals are pulled in more tightly for fluorine and neon. So there you see lithium, and then way over there on the right in the red box you see neon. So this is due to the fact that both lithium and neon have 2 orbitals. However, neon has 10 protons pulling on its second orbital, while lithium has only 3 protons pulling on its second orbital. So lithium will be much larger than neon. Okay, so let's summarize all 3 of the periodic trends we've talked about in the last 3 lessons, including this one: ionization energy, electronegativity, and atomic radius. So as we move to the upper right-hand side of the periodic table, ionization energy and electronegativity increase while atomic radius decreases. Okay, so look at these. This is what you want to know, what you want to have memorized. So if you look at the arrows going from left to right, ionization energy increases towards the right side of the periodic table, electronegativity increases, and atomic radius decreases. As you go from bottom up to top, so you look at the arrows, the upward pointing arrows over there on the right, as you go from bottom to top, ionization energy increases, electronegativity increases, and atomic radius decreases. So ionization energy and electronegativity follow the same trend, whereas atomic radius, it's the opposite. It gets smaller, the number gets smaller as you go to the upper right-hand corner. So memorize these. As you go across a row, a period or a row, more protons are added to the nucleus. The electrons are pulled in with greater force. This means the atomic radius becomes smaller. The energy required to pull an electron out, that's ionization energy, becomes greater, and the ability to pull an electron in, electronegativity, also becomes greater. As we go down on the periodic table, more orbitals are added. This makes the atomic radius larger, and the outer electrons are farther away from the nucleus. This increased distance makes both the ionization energy and the electronegativity less. Okay, so more electrons, more orbitals, more electrons means that it's more difficult for the atom. We used bromine in our previous lessons as an example. It makes it harder for them to pull in outside electrons. That's the electronegativity. The ionization energy also decreases because all of the shielding electrons, the core electrons, which are shielding the valence electrons from feeling the pull of the nucleus, they're making those valence electrons be held less tightly to the atom, and therefore the ionization energy is less. It's easier to pull one of those valence electrons in a large atom away from the atom. So let's look at a table that charts the atomic radius. So again, how big the atom is. So let's look at the first thing you look at when you want to look at a graph is you want to look at what the axes are. So the vertical axis, that's the one going up and down. It has the letters PM up there. That stands for picometers. That is 1/1 of a meter. That's on your reference sheet of it's the second one in your packet that tells you what the different units of measure are. So picometers. So these are very, very small units. And so hydrogen is very, very small. It's down there with 30. The biggest is 300 picometers. That's still very tiny, but it's the biggest. And that is something over there in the 5th row. I'm not even sure what element that is. We could actually figure that one out, but it's not important. Now on the horizontal axis down in the bottom is the atomic number. So of course hydrogen is number 1, helium is number 2, carbon is number 6, iron is number 26, uranium is number 92. So you can see the dots end right around 90 over there. So let's read this. So each column of dots is a period or row on the periodic table. Okay, so the yellow dots represent the second row. So hydrogen and helium are down there, that kind of dark dot down there in the bottom left, and then you get to the second row, and you have the second row elements. So that yellow dot that's on the top there is going to be lithium. The second one is going to be beryllium, and all the way across to the bottom dot, which is going to be neon. That's the yellow dots. Okay. So the yellow dots represent the second row, with the top dot being lithium and the bottom dot being neon. The radius decreases across the periods for the reasons we discussed earlier. More protons pulls the electrons in more tightly. The radius increase with each new row because an orbital is added. So if you look at the bottom yellow dot there, that's neon. Then when you go to the next row, the first element in the next row, that would be sodium, Na, the atomic radius jumps way up. That's the top red dot, and the reason that happens is because you've added a third orbital there. Then as you go across the third row, the more protons pulls in the electrons tighter, and so the radius becomes smaller and smaller until you get to argon down there. That's the bottom red dot. Then when you go to the fourth row, it jumps back up, and the top blue dot would be krypton. That's at the beginning of the fourth row, and so on. Now, the reason that the blue dots and the purple dots and the green dots have so many more dots is because that's when you get into the transition metals. So you actually have 18 elements across the fourth, fifth, and sixth rows. So let me read this. The radius increases with each row because an orbital is added. The blue, brown, and green columns have 18 dots because there are 18 elements in these rows. Okay, now we're going to investigate a couple of experimental techniques. We're not able to do these in the classroom, but we can do them. We can just talk about them. The first one is mass spectroscopy. So mass spectroscopy is a way of determining the mass of an isotope. So this is how they tell the weights or masses of the different isotopes of an atom, or possibly even of different atoms altogether. And it works on the principle that a lighter atom can turn faster than a heavier atom. So look at the truck and the motorcycle here, and you ask, they're going down a road and they need to make a right turn. Which one is going to be able to turn the fastest? If a truck and a motorcycle turn a corner, the lighter motorcycle will turn quicker than the heavier truck. So lighter isotope atoms can curve quicker than heavier ones. So here's the device that's used. It's a curved tube, and what it has over there on the left, first what you do is you ionize. So let's go ahead and read this. So the isotope atom is ionized so that it has a charge. Why is that important? Well, if you take away an electron from it, you're not changing its mass effectively. The mass is still the same as it was before, essentially. You really haven't changed it. But by giving it a charge, it can be propelled by magnets, by a magnetic field or by an electric field. And so what you do is you get it ionized so that it has a charge, and then you can pull it through those two plates. You see those two plates with kind of slits in them? Those are pulling the ionized atom towards them, and then the atoms go through that little slit and they travel the rest of the way down through that tube. So number one, the isotope atom is ionized so that it has a charge. Then two, a magnet moves the isotope through the tube. That's what you're seeing over on the left side there. So a magnetic field moves ionized isotope atoms through the tube. 3. The isotope atom passes through a perpendicular magnetic field that causes the isotope to curve. So that's the perpendicular magnetic field, and it's pushing on the ions, those ionized atoms, to move downward. So this perpendicular magnet causes the isotopes to curve. And 4. How much the isotope atom curves depends on its mass. The heavier isotope will take longer to curve. So if we look there, you see the light blue lines going through that tube. The one that hits highest on that plate on the bottom, that was the heaviest. It could not turn as quickly as the lighter ones, just like the truck and the motorcycle. So the heavier isotope curves the least. Now you see a graph over there, a histogram type graph over there on the right. or actually just a bar graph. And you can see that the blue line that hits highest on that plate, because it was the heaviest, so it will appear furthest to the right. We really don't have to get into the details of the axes on this. Just realize the further to the right a line is, the heavier that isotope is. The further to the left on that graph, the lighter the isotope is. So the lighter isotope will hit at the bottom of that plate in the device there, and its line will be furthest to the left. So it curves the fastest and therefore produces a line that's furthest to the left. So now we're going to study a method of determining the ionization energies. That's photoelectron spectroscopy, and it's called PES for short. So PES is a way to determine the ionization energy of an electron. The ionization energy is equal to the energy of a photon minus the energy required to make the electron travel a distance. So all we're going to say about photons at this point, we haven't gotten into the study of them, is they're little packets of light energy. So they're a given fixed quantity of light energy. That's what you can think of them as being. So a photon is a standard packet of energy, delivered by light. So ionization energy is also called binding energy. We talked about that earlier, but we don't use that term, so we are going to just call it ionization energy. The following formula gives the binding or ionization energy. So the energy of ionization, that is how much energy it takes to pull the electron away from its atom, equals the energy in the photon minus the energy of the traveling electron once it's freed from the atom. So let's just get into an example and you'll see what that means. So here's electron number 1. This is obviously a lithium atom. We're not counting the neutrons here because they have nothing to do with this discussion. So there you see the 1 valence electron for lithium. It's in the second orbital, so we're going to just call that electron number 1. So let's assume that a 20 joule photon, so a little packet of energy that has 20 joules of energy, strikes that electron. Then the kinetic energy, the energy of the motion of that electron that's flying away, they have devices that can do that, and it's determined that that kinetic energy, E kinetic, is 15 joules. So that electron had 15 joules of energy flying away. You don't have to understand how they measured that or how they figured that out. They're just able to know that. So the 15 joules of kinetic energy is required to make the electron number 1 travel this far. So they just, how far the electron flies will tell them how much energy it had. So if the 20 joule photon caused electron number 1 to travel a distance that the scientists knew required 15 joules of energy, so the kinetic energy, 15 joules, required to make electron number 1 travel that far. That was on the last slide. There it goes. So there was 20 minus 15 equals 5 joules of energy holding the electron to the atom. So 5 joules is the ionization or binding energy of that specific electron. So 20 joules of energy, let's follow this, let's think about this. 20 joules of energy was absorbed by the valence electron, the one that flew away, which then had enough energy to escape from the atom and fly a distance that required 15 joules of energy. So this means that 5 joules of the 20 joules that came in from the photon, 5 of the joules was needed to escape the atom. That's just to break away from the atom, even just a little bit. It required 5 joules of energy. So remember, you put 20 joules into that electron, it takes 5 joules to break it away from the atom, and then the other 15 joules go into allowing it to fly out in space like that. So that 5 joules that it took to break that electron away is called the ionization energy. Okay, now you have that ionized lithium atom there. And if a 20 joule photon caused electron number 2, so that's electron number 2, we're going to just identify that one as being electron number 2, to travel a distance that required 8 joules of energy. So that electron flies out, and it flies a distance that scientists know can be measured to require 8 joules of kinetic energy to make that electron number 2 travel that far. There it goes. So there was 20 minus 8 equals 12 joules of energy holding the electron to the atom. We discussed in an earlier lesson why those inside core electrons don't require more energy to pull them away. They're more tightly held to the nucleus. There's no shielding electrons. We talked about that before. So again, follow the logic here. You put a little packet of energy into that electron that's worth 20 joules. Okay? The electron then flies a distance that requires 8 joules. So that's a difference of 12. What happened to that 12? The 12 went into simply breaking that electron away from its atom. Not traveling any distance, but just enough energy to escape that atom. So the 20 joules coming in, 12 of it was used to break the electron away from the atom, and the remaining 8 was free to allow the electron to fly through space. So 12 joules is the ionization energy. And that takes care of that lesson. All right, so in the last 3 lessons, we've studied the periodic trends, what are called periodic trends. How does electronegativity, ionization energy, and atomic radius change as you move up and down and right and left on the periodic table?